Everyone hear me?
Yeah, that's much for the room.
Okay, gotcha.
Okay, I think we'll get started. So I'd like to welcome Matt Ahrens back to Brown. Matt graduated in 2001. While he was here, he was a 167, 169 TA. Matt went on first to Sun Microsystems. Sun was purchased by Oracle. Matt worked very briefly for Oracle and then went on to Delphix and where he is today.
Thanks. So I took this class in 1998. This is what the website of the entire university looked like back then. So I'm very honored to be here again talking to you guys about some of my work on ZFS. And the projector died. All right, well, I guess you guys can see this one. Just one note about this webpage. One of the most prominent features of the Brown University webpage is directions to Brown. This predates Google Maps. It actually also predates Google, the company. But there was one company that did provide online mapping services in 1998. Does anybody remember the name of it? Yes, MapQuest. And does anybody remember the name of the company that provided MapQuest? Cartographic Services. Later changed their name to MapQuest. All right, enough trivia. This is what I'll be talking about today, a little bit of history and background on ZFS, and then we'll be talking about three unique aspects of ZFS, snapshots, space allocation, and RAID-Z. So how did ZFS come to be? So after I graduated from Brown, I went to work for Sun Microsystems. Myself and Jeff Bonwick, another engineer at Sun, we started working on ZFS. ZFS was open sourced in 2005 as part of the Open Solaris project. Then in 2010, Oracle acquired Sun and basically put a stop to everything that I just mentioned. But because ZFS is open source, we were able to pick up that code and continue the code from Open Solaris in the Illumos project. And ZFS is also ported to other operating systems like FreeBSD and Linux. It's available by default in Ubuntu today. And I started the OpenZFS project in 2013. The goal of that was to bring together people working on ZFS that are working on all these different platforms in different companies. So ZFS has been used in production systems for over 10 years. And it forms the core of products offered by these companies. I've left some information in here in case you want to reference the slides later, but I'm not going to read them. So ZFS combines the functionality of a file system and a volume manager. But we've kind of reworked the internal interfaces. So the interface between traditional file system and volume manager is just a block interface. So from the file system's point of view, the volume manager just looks like a disk. In ZFS, the knowledge that there are multiple disks and how those disks are arranged is available all the way up the stack, although we don't use that information all the way up. The main point of differentiation here is that what we call the SPA, or storage pool allocator, it provides a lot of the similar services to a volume manager like RAID, but the interface to it is more like malloc and free. So when the upper layer, called the DMU, wants to write some data, it just gives that data to the SPA and says, please store this data securely, redundantly, with whatever these settings are, and then give me a token that I can use to get that data back later again. We call the token a block pointer because, among other things, it tells us the location on disk of the where the data is stored. But the SPA is actually doing the allocation. So it knows where the free space is, it knows where the allocated space is. It also can handle things like compression, in the future encryption. Yeah, that's all that I'll say about that. So one of the cool things that we wanted to do with ZFS is provide ease of administration. So thankfully, probably most of you are not familiar with enterprise storage systems, but they're very difficult to set up and administer. And if you've ever used like even a software volume manager, having two different pieces of software, the volume manager and the file system, to administer is quite a burden. So we wanted to make ZFS easy for administrators to express what they want to do. And one of the things that we did was we redefined what a file system means. So in a traditional setup, there's a file system. There's one file system that sits on top of these disks. In ZFS, we can have many file systems, which is basically like many instances of this layer and above. And each of those file systems is just drawing storage from the pool as it needs it, and then giving it back to the pool as it's done with it. So that's done on a very fine-grained basis. Just each individual block of a file is allocated and freed back to the pool as needed. And because of that, the file system becomes the administrative control point. So the main idea here is that you can use, you can set properties on file systems, and those properties are inherited down to children file systems. So like if you want to share something out over the NFS protocol, you can set share NFS equals on, and then all the file systems underneath there will also be shared over NFS. You can also say like, oh, this guy's home directory, like he's using too much space, let me compress it using gzip. We also made it easy to like add storage as the system is running with zpool add, a bunch of other cool stuff. Okay, so ZFS is a copy on write file system. This is similar to other file systems that I think you guys have learned about. It's also called shadow paging, used in other file systems like NetApp's Waffle. Simple idea, you have a tree of blocks, so everything in ZFS is in this tree of blocks, similar to other file systems. If we want to modify these two data blocks, instead of overwriting in place, we write it to new locations on disk represented by the green blocks. And then we have to modify all the indirect blocks up the tree, all of its ancestors. And then finally, atomically overwrite the root of the entire tree. So the nice thing about this is that you get snapshots for free. All that you have to do is save the old root pointer, and then we have all of the old data pointed to in that tree. So next, I'll be talking about how snapshots really work. So there's three problems with snapshots, or three points where we need to interface with snapshots. First is creating them. We already saw how that works. You just save the root block pointer. Second, when a block is removed, we need to figure out if we can free that block. So by removed here, I mean like if you have a file and you remove the file, the live version of the file system doesn't reference that file anymore, but it might still be part of snapshots. So in ZFS, the way that we do this is in the block pointer, it has not just the location of the data on disk, but it also has the time that that block was written. And because blocks are never overwritten in ZFS, because it's copy on write, the time that it was written is also the time that it was allocated. So to figure out whether a block is part of a snapshot or not, all that we need to do is look at the time that it was written and compare that to the time of the most recent snapshot. So if the block was written after the most recent snapshot, then no snapshots can reference it, and therefore we can free it. So in this example, this orange block was written at time 37. So here, this is the block pointer that's telling us information about this block. If we no longer need this block, we look at the block pointer. It tells us created at time 37. The most recent snapshot was at time 25, so therefore the snapshot doesn't reference it. But if we don't need this green block anymore, it was written at time 25, which is less than or equal to the previous snapshot, so we know that that snapshot does reference this block, and therefore we can't free it. Great. So the remaining aspect of snapshots is when we delete a snapshot, how can we find the blocks to free? Well, this is a lot trickier, but I promise this trickiness will be worth it, because other ways of implementing snapshots are pretty horrible. There's a lot of like linear time algorithms in here and space usage, and a lot of this is why a lot of previous snapshot systems have to put limits on the number of snapshots. In ZFS, part of the ease of use of ZFS is that we wanted to remove the limits on numbers of snapshots, numbers of files in a directory, all those kinds of things, so that people who are using ZFS can use it the way they want to use it and not be constrained by the implementation artifacts. Okay, So when we delete a file system, we have to find all of the unique blocks and free them. So the unique blocks are the blocks that are referenced only by this snapshot. And so ideally, an optimal algorithm for this would only take time proportional to the number of blocks to free, because there's no way to be faster than that. We have to free every block. Ideally, our algorithm would be able to find those blocks to free using a small number of reads from disk. So probably we aren't going to be able to fit all of the metadata of the system in memory. We're going to have to do some reads from disk. So in ZFS, there could be, or in any file system, there could be a large difference between like an O of n algorithm where it has to do n reads, and an algorithm where if the data is stored compactly, we might be able to do like 1,000, we might be able to go 1,000 times faster than that if we can aggregate all of the relevant data into a small number of blocks. So thankfully, the block lifetimes in ZFS are contiguous. So this means like a block is born, i.e. We write it to disk, it's referenced by some number of snapshots, and then the block is killed. And no snapshots after that reference it. The block can't come back to life in a later snapshot after it was dead. So therefore, the unique blocks are the blocks that are not referenced by the previous snapshot and not referenced by the next snapshot. But we don't care about any of the other snapshots because we know if it's not referenced by the previous and next, it can't come back to life in some other snapshot. So I'm going to be talking about 3 algorithms for snapshot deletion. The first is the turtle algorithm. So in this algorithm, it's pretty straightforward. The way that we find the blocks to free is we traverse this tree of blocks, which we saw previously. We look at the birth times and we see, okay, is the birth time before the previous snapshot? If so, it's referenced by the previous snapshot, so we can't free it. And one of the nice things about this is that we don't have to look at every indirect block. For example, this indirect block was written at time 19. And time 19 is before the previous snapshot. So therefore, all of the blocks underneath that also must have been written at time 19 or earlier. So therefore, we don't even have to read this indirect block at all. But we still need to figure out if the block is referenced by the next snapshot. So to do that, we can just read the same object, read this from the same file and offset in the next snapshot and see, oh, is this block pointer identical to the one that I have? If so, it references it. If not, then it doesn't reference it. So this algorithm is proportional to the number of blocks that were written since the previous snapshot, because that's going to tell us how many of these indirect blocks we need to read. But it could be pretty bad because it's O of this, but it might be that every indirect block points to only one data block that we actually need to free. So in order to free one data block, we might have to read a whole indirect block here, and then also read the same kind of corresponding indirect block in the next snapshot. So 2 reads just to do 1 free. So the downsides of this are, like, maybe you read 1,000,000 blocks and you free nothing because the next snapshot is identical or mostly identical to this snapshot. And even if you don't have that problem, like I said, maybe you have to read 2 blocks to free 1. And the problem with this is that if you have a hard drive, it can do about 200 random operations per second, and it can write about 200 megabytes per second. Well, if we are using an 8K block size, and it takes us 2 reads in order to free 1 block, then we can free at less than 1 megabyte per second, but we can write 200 times faster than that. So unless you're continually adding storage to the pool, eventually you're going to have to free stuff at the same rate that you are writing it, and your performance is going to be throttled by how fast you can free this, and it's going to be throttled to like less than 1% of the actual potential performance of your hardware. So pretty awful. Okay, so the next, the bunny algorithm, the next algorithm, the main idea here is that we're going to keep track of these no longer referenced blocks in some auxiliary data structure. So we call this the dead list. Every snapshot and every file system keeps track of this dead list. The dead list is just an array of block pointers that we store on disk. We keep appending to it. And it tells us the blocks that are referenced by the previous snapshot, but not referenced by this snapshot or file system. So we can see that diagrammatically here. So for example, if you take this snapshot 3, its dead list, it is blocks that are referenced by the previous snapshot, not referenced here, and they might or might not be referenced by earlier snapshots than that. So how can we use that when we are deleting a snapshot? So let's take the example of deleting this red snapshot. We can look at the next snapshot's dead list, which is, again, blocks referenced by this snapshot, maybe earlier ones, maybe not, and not referenced by the next snapshot. So we can look at all of those blocks and separate them out based on their birth time. So if the birth time is after the previous snapshot, then the block's birth time lifetime looks like this. It's only alive just during this snapshot that we're trying to delete, so we can free it. And the other snapshots, their birth time is before the previous snapshot, so they're still going to be referenced by this one, so we can't free them. And then to make sure that we leave the dead lists in a consistent state for when we do a subsequent deletion, we need to merge our dead list with the kind of remainder of the next snapshot's dead list. So how long does this take? Well, as we saw, we don't have to look at the tree of blocks. We don't have to look at the next snapshot. We just look at the next snapshot's dead list. So it's however big the next snapshot's dead list is. This is going to be the number of blocks deleted before the next snapshot, which is kind of similar to the previous turtle algorithm, because in the long run, like the number of blocks deleted is going to have to be similar to the number of blocks created. But the big win here is that this dead list is stored compactly. So every block that we read from the dead list has 1,024 block pointers in it. So this algorithm is up to 2,000 times faster than the previous one. But it could still take a long time and free nothing, because we might find that, of the next snapshot's dead list, there's like 1 million blocks like this that we have to move, and only a handful of blocks like this that we actually have to free. Okay, so now we get on, and I should mention this first algorithm, we never implemented that. It's too horrible. This bunny algorithm was the state of the art until 2010 when we implemented the Cheetah algorithm. So this is an extension of the previous algorithm mentioned. So we're still using dead lists, but we divide the dead list into sublists based on the birth times. So we have one sublist per earlier snapshot. So in this example, we see like all of these blocks are part of snapshot 5's dead list because they're all referenced by snapshot 4 and then not snapshot 5. But we've divided out the blocks based on their birth times such that the ones whose birth times are in this range go into one list, the ones in this range go into a different list, and so on until we get to the ones that have existed since the beginning of time, or since the first snapshot. So now to delete a snapshot, let's say here we're deleting snapshot 4, we need to only iterate over these sublists, and if the sublist, if the minimum transaction, if the minimum birth time of this sublist is after the previous snapshot, then all of the blocks are like this, and so we can free them. These other sublists, we need to merge with the remaining, snapshot 4's dead list. But we can, if we, as I'm calling these lists, they're not actually linked lists. They're like array lists in that they're stored as arrays. So we don't want to have to actually like copy all of this onto the end of this list. But if we append them by reference, by just adding an entry that says, hey, everything that's on this other array is like logically part of this array, then we can do this operation in time. Each append is constant time. So the overall performance of this is, merging all these lists in is O of the number of sublists, which is basically like the number of snapshots that were that existed when this snapshot was created. So you can think of it as like the average number of snapshots. We have to move that number of sublists. And then plus, of course, the blocks that we actually have to free, which were all on this list. So if we compare that to our kind of optimal goal, the difference is only the number of sublists, which is typically much, much less than the number of blocks to free, because maybe like 1,000 or a couple thousand snapshots would be a lot, but the number, you could easily have millions or hundreds of millions of blocks that you need to free. And practically speaking, using the same example, kind of hard disk and 8 kilobyte block size, we're able to free at over 1 gigabyte per second, which is much faster than the disk can write. So at least snapshot deletion will not be the bottleneck of your entire storage system. Cool. So next, we talked about these dead lists and sublists and storing those. I want to talk a little bit about what that looks like inside of ZFS. So as I mentioned previously, there are ZFS can have lots of file systems inside of one storage pool. Each of those file systems is called an object set. And there's this meta object set, or MOS for MOS, which has all the pool-wide metadata. So information about what snapshots exist, what their dead lists are, the relationships between the snapshots, like their ordering, is all stored in this meta object set. Also information about like what space is allocated and what space is free is stored up here. And then within each object set, including the MOS, there's an array of what we call dnodes. This is a data structure that's like corresponds to each object. An object is just like a file. And each of these triangles kind of corresponds to a tree of indirect blocks. This is like a more detailed picture of that. I also want to show you a picture of the block pointer. So in a lot of previous file systems, the block pointer was basically just the offset on disk of where the data is stored. In ZFS, and a lot of times that was like, in the old days, that was 32 bits. Here, the offset is almost 64 bits, and then we have 16 words, 16 to 64-bit words. So the block pointer is much, much larger. We call it a luxury class block pointer because it has all this stuff in it. So I mentioned ZFS, you can add lots of disks to the pool. So we need to tell, like, each piece of data is specified by the device ID or disk ID, and then also the offset within that disk. And we actually have 3 different places that the data could be stored. For all like metadata in ZFS, we actually store multiple copies of it, and this tells us where all of those copies are. We were talking about like the birth times of blocks. That's stored here in this logical birth time field. And then in ZFS, we also checksum all of the data on disks, and that's stored in the block pointer. That means that the checksums form a Merkle tree of checksums where each layer is checksummed by the block pointer above it. And so, we know that the entire tree is correct, but that means even if you have weird kind of storage errors like misdirected writes where we tell the disk to write some data, and it writes the data, it just doesn't write it at the offset we told it to. So the data like on disk is kind of self-consistent, like each block is individually self-consistent, but it's not the right self-consistent block. Having the checksum in the block pointer allows us to detect that kind of error. And if the data that we're storing in this block compresses really, really well, then we can actually get rid of the, we can actually not point to the data at all, but rather embed the data directly into the block pointer itself. So this is like if it compresses down to like 100 bytes or less. And you might wonder, like, when does that ever happen? If you're using, say, like an Oracle database, when you create, when the Oracle database creates a data file, it starts by initializing that file. It initializes it by writing a little header onto every single block. The header just says, like, I'm part of file number X, I'm an Oracle data block, I'm block number 10. And the next one says exactly the same, except I'm block number 11. Well, that little header is super tiny, so when we compress the whole block, it can fit in this block pointer. So this is great. We get better space efficiency and like better performance when you're like reading it. You don't have to go read it from another block on disk, so less IOPS. But the true win here is that Oracle DBAs like to benchmark their storage by creating data files. So when they create the data file, they're sending down like a terabyte of data, and we're like, great, we totally stored your terabyte of data. It just compressed really, really well, and we only had to store this metadata. Cool. So next I wanted to talk about compression. Sorry, I want to talk about space allocation. But what's unique about the requirements of space allocation in ZFS? So in ZFS, we have built-in compression. The compression happens at the block level. So in this diagram, like the DMU is thinking that, great, I have an array of 4 block pointers. They each point to 128 kilobytes of data. But when we send it down to the SPA to store it, the SPA compressed that data. They compressed each block independently, and then allocated just the amount of space that's needed for the compressed size. And you can choose different compression algorithms like LZ4, which is really fast, gzip, which is really slow but compresses very well, and other kind of weirdo ones. So because of that, and because of other things, we have variable block size, which is great because we get like transparent compression. We can change the block size to match the block size that a database is using, for example. But the downside is that it means that we have variable allocation sizes. So we can't just say like, we have a pool of 4K blocks, and you can ask me for a 4K block, and I will give you one. Or you can ask me for 10 4K blocks, and I'll find 10 4K blocks, but they'll just be like wherever I felt like finding them. They might be contiguous, they may not be contiguous. In ZFS, it's more complicated because when we want to allocate 97 kilobytes of space, we need to find 97 contiguous kilobytes. There's some exceptions where you can like add another layer of indirection, but then performance is bad. So we want to avoid that as much as possible. So in other words, we need to be able to find runs of contiguous free space. And we can't just fit all of the allocation data in memory at once. So we need to have some way of like storing this on disk, maybe having a different representation in memory. Because if we were to try to keep it all in memory, it requires like about 3 gigabytes of memory for every terabyte of disk space in kind of the worst case where you have a lot of fragmentation. And we want to take advantage of the fact that ZFS is a copy on write file system, which means that whenever we're writing, we're allocating, which means that whenever we're writing, we can choose where we want to write. So we want to choose to write stuff as contiguously as possible so that even if the application is sending us writes to like logically random offsets of files, we can take those and put them on disk contiguously so that the writes go really, really fast. Okay, so we use an on-disk. So first of all, we divide each disk into 200 chunks that we call metaslabs. You can think of this as just like the first terabyte of the disk, the second terabyte of the disk, or maybe I guess the first gigabyte, the second gigabyte, third gigabyte. The space map is a log of all of the allocation and free operations. So it's really just like 3 fields, like is a bit telling us is it allocate or free, the offset, and then the length of the run. We just, like as we allocate and free stuff, we just append more entries to the end of this. And it just keeps growing forever until we fix it up. And the space map is stored in the MOS with the other pool-wide data structure, metadata. But this data structure is really, really inefficient to allocate from. If we want to find where the free space is, we'd have to guess, maybe there's free space at offset 7. Okay, now read every one of these entries until it tells us, until we find the information about offset 7. So when we want to do allocations, we load this space map into a data structure that we call a range tree. and this is an in-memory data structure. It's a balanced binary tree, like an AVL tree. It tells us all the free segments. So each node in the tree tells us this range is free. It's available for allocation. And we actually put these nodes into two different trees that are sorted in two different ways. So first, we have a tree that's sorted by offset. So remember, like to read, like the lowest node is here, then this would be the middle node, and then this is the node that sorts the highest. So, and the reason that we need this sorting of the tree is that we want to be able to consolidate adjacent segments. So for example, like if somebody came in and said, I want a free offset 1 and 2, then we could find that node is like, this is the previous node, that's the next node, they're all adjacent. I can replace all these with just one node that says 0 to 3 is all free. And then we have a second tree that's sorted by length. And the reason is that we want to be able to find the segment that has that's like the largest run of free space to do allocations from. So here, like the largest range is 5 to 7, its length is 3, and then these two that have length 1 each. Cool. So in ZFS, we batch up all of the write operations into groups that we call TXGs, which stands for a transaction group. So every few seconds, we are flushing out we're writing out all of the dirty data in one of these transaction groups. So while we're writing it out, we keep track of 2 additional range trees that tell us what space has been allocated in this transaction group and what space has been freed in this transaction group. And then as we're finishing the transaction group, we're going to append all the entries from these range trees to the space map. Obviously with the allocated ones marked as allocations and the free tree marked as frees. So a couple of interesting things about this. If we're not allocating from a metaslab, we don't have to have it loaded, right? If basically the consumer is telling us these blocks should be freed, all that we have to do is append those ranges to free to the end of the space map. But if we want to allocate, we have to load the space map into the in-memory range tree. Okay, another cool thing I'll mention here. I think we're doing okay on time. So the space maps are stored in the MOS, which means that like as we're writing the space maps, we have to allocate space to store those space maps. So you have this problem of like convergence where we might say, great, like I'm freeing this stuff, so append it to the space map, and then I have to write out the space map, and then that has to allocate more space. Then we have to append more things to the space map, which means we have to allocate more space for the space maps, and this could go on forever. But we short circuit that by saying that while we are, when we're writing out the changes, if we've already written out this logical block in this transaction group, then we can actually overwrite it in place. And it's okay, it's safe to do that because nothing else references that. Nothing in like the stable state of the pool references that. It's still part of the currently syncing transaction group that nothing depends on yet. So overwriting that data is okay. So then like as long as the space map doesn't grow to require like a new block, then we can keep changing and appending entries to it within the existing allocation that we did for this particular transaction group. And then lastly, so I said we just keep appending to this forever, and it grows forever until it takes up all the space in the entire storage pool. No. So what we do is when we have the space map loaded into the range tree, we know the range tree tells us basically what's the minimum number of entries that we could use to represent this data structure, right? Like however many nodes there are in this tree, if we write it out to the space map, that's how many entries there will be in the space map. So we can check and see like, okay, if we get to the point where the on-disk representation is twice as large as the optimal representation, then we can throw away this version and write out a whole new representation of it based on the in-memory loaded range tree. Great. So lastly, I wanted to talk about how ZFS implements RAID. So traditional RAID, you've learned about this. Stripe is physically defined, meaning that the parity is at fixed locations on the disks. And partial stripe writes are awful, both for performance, because like one write could turn into 2 reads and then 2 more writes in order to update the parity correctly. And they're not crash consistent, because if you crash in the middle of those 4 operations, you're going to leave the parity inconsistent, and you've damaged not just the block that you were trying to write, but any of the other blocks that are part of that stripe. Even if they weren't being modified, you've left them unprotected. And there are a bunch of fixes for this. They all involve expensive hardware and complicated logic. So with RAID Z is like kind of a different way of approaching this problem. That's really only possible because the RAID layer also is aware of and handles space allocation. So we support single, double, and triple parity. So you can have like up to 3 devices fail and still be able to recover. It eliminates this RAID 5 write hole that I mentioned. You don't need any special performance. How do we do it? Well, you just can't do any partial stripe writes. And the way that we accomplish that is that rather than having the stripes be like fixed size and the parity be at fixed locations, the parity is actually part of the allocation that we do for each logical block. So each logical block includes its data and its parity. So different sizes of logical blocks would have different amounts of parity. The kind of downside to, one of the downsides to this is that odd sized blocks could use more than expected amount of parity. So like if you have RAID Z1 that tolerates 1 failure and you have 4 disks in it, you might expect, like if you did RAID 4 or RAID 5 with this, 1 disk would be used as parity and the other 3 would be used for data. If you have large blocks, then that will be the same for RAID Z. But if you have a smaller block, then we might have a block where, like, if the block is only 2 sectors, then we're going to have to allocate 1 sector of parity just for those 2 sectors of data, rather than 1 sector of parity for every 3 sectors of data. So you can see that illustrated here. The most kind of degenerate case is like, so here, like, each color is a different logical block. So like this is the most degenerate case where the data is just 1 single sector, and then there's 1 sector of parity. So this is like the same space utilization as mirroring, right? You have as much parity as you have data. But then for larger blocks like this one, you have kind of close to the optimal expected situation where here you have like 4 pieces of data for every 1 piece of parity, and the only exception is for this last like row of the block. The other kind of downside to this is that because each logical block is spread out across all of the disks, to read a block requires reading from all of the disks, or at least all except for the parity one that has the parity for it. So the random read performance on RAID Z is kind of similar to the random read performance of 1 disk within the RAID Z group. Whereas with traditional RAID, if you kind of arrange everything just right, then you're able to do random reads where each read is just reading from one disk in the RAID group. Cool, doing great on time. ZFS is still under a lot of active development. We have a conference every year called the OpenZFS Developer Summit that's put on by Delphix. It's usually in the fall. We've been having it for about 5 years. And usually we have people talking about like work in progress or ideas that they have. A lot of this is stuff that's coming up. So a few of those things are we're working on adding on-disk encryption so that you can do encryption natively within ZFS. You can have like different file systems encrypted with different keys or different algorithms. Also, we want to be able to replicate data from one storage pool to another while maintaining this encryption. So you can have it encrypted end-to-end from the source pool to the target pool. Channel programs is a project that allows you to do compound administrative operations. Like I want to create a file system, set these 3 properties on it, and delete this other file system all at the same time. Meaning like you want it to be atomic and perform well. We're working on improving the performance of space allocation even further. And then another big project is device removal. That we finished implementing this, but it isn't yet upstream in the OpenZFS distributions. But this would allow you to actually remove disks from the storage pool, migrating all of the data off of that disk onto the remaining disks. So if you want to read more or about ZFS on our website, there's like tons and tons of links. And I took a few out here that I think are kind of the most highest quality things that you might be interested in. So these are all specific features of ZFS. I have a whole hour-long talk just about space allocation. So this is like the mini preview of that. And a lot of these talks are by other Brown grads. Adam Leventhal was my year. He wrote a bunch of blog posts. And Joe and Sarah were interns with Delphix, and they gave talks at the OpenZFS conference as well. If you're more interested in like overview of like what is ZFS, kind of compare and contrast with other file systems, there's a great book written by Kirk McCusick. Kirk actually implemented UFS, which is like the original Unix file system. So it's a great honor to have him like explain the next generation Unix file system. I worked with him a little bit on that chapter of that book. I have a 2.5 hour lecture that is about the read and write code paths and actually goes through, walks through the code so you can see what's happening there. But it also has about a 45-minute intro to all different aspects of ZFS. And Kirk actually also has like a video that goes with his book if you'd rather watch a video. If you're interested in like, how did ZFS come to be? Like, what is this open source thing? How does it work? There's people working at all different companies. I gave a talk about kind of the history of ZFS and how it came to be, how some of the features came to be. Jeff Bonwick, who is the co-creator with me, he hasn't been working on ZFS since he left Sun, but he came back to the Developer Summit a couple years ago and gave a great talk with some anecdotes from the early days of ZFS. And then I also wrote a paper about founding the OpenZFS collaborative community. Great. So we have a few minutes left. Any questions?
Yeah. So you had a slide showing the operating systems on which ZFS can run. Notably absent there is OS X.
Yeah, so actually, notably absent is OS X, but it actually does run on OS X. So there's actually a port of ZFS to macOS. It's unofficial. So several years back, Apple was working on a port of ZFS to OS X, but they later abandoned that, largely due to political reasons. But there have actually been at least 3 efforts to port ZFS to OS X. The Apple one, there was one by a former Apple employee who had worked on the port, then left Apple, redid the port on his own, but then that was sold to another company, which then kind of killed it. But now there's a third one which is done by a guy out of Japan, who, which is like totally, he's like totally part of the community. It's not owned by any company, totally free and open, and it works very well. But I didn't include it on this slide just because it's not like mainline, and it's not in as widespread use as these other operating systems. Other questions? Yes.
You mentioned that when you were writing blocks to disk, you aim to have one contiguous span of disk, right? Even if the blocks are separate with no file or something like that. That seems like you're sacrificing read speed for write speed, because then when you read, you have to jump around more often. Was that a trade-off that you considered, or is it just that makes read and write speed closer to each other?
Yeah. So this is kind of this is a trade-off in copy on write or shadow paging file systems in general, where because we've chosen to write to a new location, I guess you're asking kind of for the motivation. I think that the motivation, personally, I think that the motivation is really so that you can implement snapshots and all these other features. Like, there's a bunch of other things that kind of also depend on copy on write, and I see that as a larger motivation than the performance aspect. But yeah, like as you mentioned, you're trading off, like, if you're doing random, if you're doing everything sequentially, right? If you just have like video files and you're writing them sequentially and then reading them sequentially, then there's no trade-off. Like, it's just everything is great. If you have like a database and you're updating to random locations and then you're reading from random locations, then again, like, you're doing random reads, so it's really no different than if it was laid out like a traditional one. The place where you have the trade-off is if you're doing random reads and then you're doing if you're doing random writes and then you're doing sequential reads. So this is like you're using a database and then you're like doing a full table scan to find something or do some data warehousing operation. So they're like ZFS and copy on write file systems have this big win of like you're doing the random writes because they go really fast because it's sequential. But then when you do this sequential read, we have to seek the head all over the disk. The reason I think that this performance trade-off is acceptable is because when you're doing the sequential reads, we know what you're going to do. Like, you're reading this sequentially, so we can prefetch really, really far into the future, and you can actually get like 2 to 5x better like random read performance, quote unquote random read performance, by queuing these far in the future and then sorting them based on the offsets on disk. So like, we know like here's the next 10,000 reads that you're going to do, sort them by offset on disk, and then just sweep the disk head once over it. So and like with traditional systems, you can do that for random reads. You can do that there, but when you're doing those random writes, there's no way around it. Like, there's no mitigating factor. Yeah.
When making backups of a disk that's using ZFS, are there any special considerations? Can we use snapshots to optimize that process?
Yeah, so there's kind of 2 ways to look at doing backups. One would be like using ZFS native capabilities, where it's like, I'm using ZFS, I want to back that up to somewhere, and then I'm gonna like always be restoring it to another ZFS. You can use a feature of ZFS called send and receive. There's a talk about that. Replication with send and receive. Dan Kimmel, who is also Brown grad, gave that talk. So with that, it takes advantage of like all the internal ZFS data structures. It works really well. You can do incrementals really fast. It's much, much better than like traditional ways of doing incremental backup. But you're only going to be restoring it onto ZFS. If what you want to do is like a backup like underneath ZFS, where you're just like looking at the disk contents and copying them off, the only consideration there is that ZFS can consume multiple disks. So if ZFS is just consuming one disk, then you can do this backup like it's like fine, it just works. But if you have multiple disks, then you need to back up a consistent point in time across all of the disks. This has been a little bit of a challenge for some like cloud providers, and we're actually working with Microsoft to add some capabilities into ZFS to basically like kind of freeze ZFS while you take snapshots of multiple virtual disks without actually having a performance impact due to that freeze. So you're still able to do writes, but we aren't updating the global Uber block that references everything. So you're still getting both performance and consistency within that time period.
Does that apply to a Windows version of this?
No, so that's for, there's no Windows port that I'm aware of. This is working with Microsoft on their Azure Cloud stuff. So you can run Linux on Azure Cloud, and Microsoft has actually been really working a lot with the Unix communities, with Linux and FreeBSD, on getting those operating systems to run well on Azure Cloud, and obviously that includes ZFS.
We have time for one more question.
Can you talk a little about the ideological paradigm of thinking of things as file systems as opposed to files and directories? Or like having that be like the main? Yeah, so like the file system as the administrative control point, and like file systems are really cheap. So yeah, so with ZFS, because you can do ZFS has so many capabilities and features built in, we didn't want to make you have to apply all of those to the entire storage pool. Like to say, great, you have snapshots, so you can snapshot the storage pool. We wanted to make it flexible so that you could say I have different types of data that are logically different in the way that I think about them. Like I have people's home directories, and then I have this production database, or I have home directories, and then I also have my video production files. And I might want to have different retention policies for these different things. I want to take snapshots of people's home directories once an hour and keep a week's worth. But for the video files, I want to take them every day and keep them for a year. And they're changing much more slowly, so the space usage all works out fine. So that's really where the idea of using the file system as the administrative control point came in, is because we want to let you combine all different kinds of data together into one storage pool and set them up differently, like having controls. So you can say you might use too much space, so I'm going to put a quota on your usage. You're very important, so I'm going to give you a reservation so you can use lots of space, and all the the students can't infringe on the professor's space usage, for example. So file system, the idea of using the file system for that has worked out really well. In part because file system corresponds to a mount point, and people are already used to the fact that you can't hard link across file systems. So it creates a very clean separation of what data is part of this group of data that I'm telling I want to all be compressed or all be snapshotted or whatever.
Okay,
Thanks.
thank you very much.